Hello student, this is another example that we are going to work on the analysis method that's called the consistent deformation method. And as you may see from the problem we have now, our beam have the support of roller at A and the pin at B and the roller also at C. And if you consider this, you can see we have the two reaction at B and one at C and also another one at C. So the total reaction of this beam, known reaction, is going to be four of them. It's going to be A sub Y, B sub Y, C sub Y, and also B sub X. And as you may see, there is no horizontal force, so the B sub X is 0 by the summation of X sub X equal to 0. Okay, and you have four unknown reaction, but you have three equation of equilibrium. So by doing this, you'll be going to have the degree of indeterminacy, you may call this one degree of indeterminacy of what? Of 4 minus 3 is 1. Okay, and since the consistent deformation method is can be classified as the first method to be used to analyze statically indeterminate structure. By the first method, that means we going to use the force as the unknown to show this. So based on this, you have this one for the A sub Y, this one for the B sub Y, this one for C sub Y, and this one for the B sub X. And you may also consider what the problem give to you is the diffraction equation. Okay, since the problem give to you the diffraction of the beam occur due to the simple beam, that means they have the simple support at the end of the beam. So by considering this, we will set the reaction B sub Y as the redundant force. This is redundant force. And then if you set this B sub Y as the redundant force, so your beam gonna be like this. Let's see, this is 15 meter, this is 20 meter. Let's set 1 meter equal to 1 millimeter. So our beam gonna have 35 millimeter long, and this portion is 15. So this is going to be A, this is going to be B, and this is going to be C. And the support here is the roller. And you have what? You have the applied force. That is going to be the uniform load here. And also you have the force here. And what we have the B sub Y as the redundant. Okay, and also we have this one is 15 meter, this one is 10 meter, and this one is 10 meter. And what we have is this beam is going to have the B sub Y as redundant. If we know B sub Y, you can determine the reaction at C sub Y and at A sub Y. So you can answer to this. Okay, and before you can go further, we will use the second. We will set up the reaction B sub y, and the second we're going to write down the compatibility condition at what now, at B. Okay, consider let us consider the compatibility condition at B, and then if you set like this, and then you use the principle of superposition. Use the principle of superposition. Okay, the beam here, the beam can be considered or separated into two cases. Okay, one is going to be the beam that's going to what, to subjected to the applied force. So this is going to be the beam, and it's going to plus another beam. Okay, and then if we set this is going to be aligned together. This is going to be the roller, and if you make it to be very correct, this is supposed to be the roller also. Okay, because you still have the B sub y here, and this is going to be the roller, and this is going to be the same thing, the roller and the roller and the horizontal roller. What happens is this beam will subjected to the given load, and if you put this one in back, it's going to be a little bit more clearer. Okay, we call this as the primary beam. This is going to be the primary beam. The primary beam is the beam that's subjected to the applied force. Okay, and it's going to plus another beam that's subjected to the redundant. This is going to be B sub y. Okay, and then we got to what? We got to consider the deformation. Consider the deformation of the beams. Okay, and we consider this. What happens is, under the applied force, this beam will deform something like this. Since this one is a roller, okay, only the rotation around here. Also, this one, rotation around here, and there is no movement. So the displacement at this point is going to be 0. And for this one, under the force, the beam may deflect something like this. And what do we have? This is going to be the vertical displacement of delta B. And for this one, the force pushing up. So this one gonna change to have the shape like this. And what happened is, it's going to have the vertical displacement like this. And since B sub y is the unknown, and let us set the B sub y to be 1. So the diffraction going to be F for the diffraction at point B due to B sub y. This is the diffraction when the B sub y equal to 1. And if the unknown B sub y applied to it, the total is supposed to be this one. Okay, and then when you consider the deformation of the beam, we got this one 0, and then equal to delta B, equal to delta B, and then V is plus, but the direction of the vertical displacement, they are opposite, so minus. Okay, and then you get F sub BB, and then B sub y, And from this, you may reduce this equation again to b sub y equal to delta sub b. And then you divide it by f sub bb. Okay. And you consider this equation, you may see that what if you can determine the displacement delta sub b and displacement f sub bb, we can find b sub y. When we know the value of b sub y, we can determine the a sub y and c sub y. See? Okay. Now, what next is we going to determine the relationship of delta sub b. Okay, this is going to be the third step. We determine the force displacement relationship, okay, of delta sub b and f sub bb. Okay, and since we have this table by using you know what is this, what method we use to solve this? By using the superposition method. The superposition method. Okay, we're going to use this to determine the displacement here, and then we can solve for delta sub b. Based on this, we come back into the problem we have. Okay, for the first one, this beam subjected to both uniformly distributed load and the point load. Okay, and let's start for the point load. That's going to be 15 kilonewton, and uniformly distributed load going to be 4 kilonewton per meter. And let's see, it's going to occur at B. So this is going to be A, this is C, and for this one supposed to be the point of B. So let's set the diffraction here is going to be delta B1. Okay, and this one downward also. You may set this one as the delta sub B2, and delta sub B is going to be the combination of these two. Okay, so delta sub B1 equal to, this is going to be 15 kilonewton. And then what we have is the total length of the beam is going to be 35 meter. And then what the A is the distance between here, this A, from here to here. So this is 15, this is 10, so the total is going to be 25 meter. If this is 25 meter, this is going to be 10 meter. And the last one that we going to determine is the X. This X is going to be what? The X is going to be this one, and that's one going to be 15 meter. So what we have is going to be 15 for the P. Oh, you don't need to consider this because it's downward already, we noted. Okay, this is going to be 15 kilonewton, and times the B is going to be 10. Okay, and times the X is going to be 15. So it's going to be divided by 6 EIL. So divided by 6 EI. What is the L? L is here is going to be 35. So it's 35. And in parentheses, L square is 35 square. And then it's going to be minus B square. Minus B square is also 10 square. And it's minus X square. So it's minus 15 square. So the total is going to be this. If you put everything into your calculator, you may pause this video and check it out. What do you get from your calculation? This is going to be 9,642.86 divided by EI. Okay. And next, we have what? We have uniformly distributed loads of 4 kilonewton. Okay, so we come here. This is going to be 4 kilonewton per meter. And L is going to be 35 meter. And the X is going to be the same thing. X equal to 15 meter from here to here. So now, just put everything into this one. Is going to be W 4 X 15 and divided by 24 EI. By 24 EI. And in the parentheses of X cubed. So it's going to be 15 power 3. And minus 2 times L times 35 and times X squared. That's it's going to be 15 squared. And then it's plus L cubed. So it's 35 cubed. And then you get this. Okay. And put everything in your calculator. You will get the result of this diffraction of 6,250. Okay, divided by EI. So if you like, you just do the summation of the delta sub B. So now you will have the delta sub B, which equal to delta sub B1 plus delta sub B2. And then you get this is going to be 9,642.86 and divided by EI. And is going to combine with this one plus 46,250 divided by EI. And finally, you get this big number of 85,892.9 divided by EI. And its direction is going to be downward. Okay. Okay. Next, we come into this. This one views the same thing as this, but we got to consider that we will set the f sub b equal to 1. So if we set f sub b equal to 1, we will have f sub bb. We have f sub bb. F sub bb equal to, if you consider this force will change the direction into this one. So the force P is going to be 1. And since the distance from A to the force is small a, okay, so we will have this one as the A equal to 15 meter. Okay, and from the load to the C is going to be B, so this one is going to be B equal to this one is 20 meter, so this one is here. Okay, and the position B is here, that is 15 meter, so that is going to be the X. Okay, X is going to be 15 meter. Okay, now you may put everything into this equation again, but this time is P equal to 1 and B is 20. b is 20, and x is going to be 15, and then that is going to divide 6 EIL, 6 EI, and L is going to be 35. And in the parentheses, okay, you may put the thing L square is going to be 35 square minus B square. B is going to be minus 20 square, and then minus x square, and then you minus by 15 square. And if you put everything in your calculator, you will get this one 1 times 20 times 15 divided 6 EI 35, and in the parentheses that is going to be 857.4 857.4 divided by EI and upward. Okay, just stop the video clips and put everything into your calculator. Now, next step, we can find B sub y. Okay, so now go. Okay, we going to determine B sub y. Okay, and the reactions of A sub y and C sub y. Okay, that's required for what we're going to put into this table. Now we start by B sub y. After we know B sub y, we can find the order. Okay, by doing this, what we have is the B sub y is equal to this one, 85,892.9 divided by EI, and then it's going to divide by F sub BB 857.4, and then EI here, cut, and then you get this for 100.2 kilonewton. That is going to be the B sub y. So we go a little bit further on this, our B sub y, and we do again as before. Just project this one. Actually, we like to draw this one, and we also have this one. The beam gonna have the applied force of 4 kilonewton per meter, and it also has this one. It's 15 kilonewton, and this is 10 meter, and 15 meter. What we have is, here is the B sub y, right? So let us move a little bit here to the position. This one gonna be 100.2 kilonewton, and we have this one for the A sub y, and this one for the C sub y. You may take the moment. Let me take the moment here. Okay, summation of the moment at C equal to 0. We're going to determine A sub y. So A sub y is positive 100 times 2. So we have how far A sub y from here is 35, right? So it's 35 A sub y. And this one rotate the same direction plus. Okay, this is going to be 20, right? So 20 times 100.2. And the opposite is this one 15 times 10 is going to be equal to 15 and then times 10. That's going to be counterclockwise. And this one is going to have the resultant force. And the resultant force of this is going to be 4 times the total of 35. And what we have here is going to be 35 divided by 2. Okay, that is going to be plus 4 times 35. And the distance is 35 divided by 2. Now, you got the A sub y. So, the A sub y is going to be what? Pause your video clips and do your calculation. You get for the A sub y 17.03. Okay, this is going to be 17.03. So summation of f sub y equal to 0. Okay, you get the c sub y up plus 17.03 plus this one 100.2 up and downward equal to 15. Okay, and this one plus 4 times 35. And now you do the calculation. You will get c sub y equal to how many? 37.77. 37.77 kilonewton is up. Okay, this one also up. Now you got everything that you're going to answer to the table. Okay, this is 37.77 kilonewton. The B sub y is 100.2 and the A sub y 17.03 and all upward. Okay, and this all of forces gonna put into this, so C sub y is gonna be 37.77 kilonewton, and this one going to be 100.2 kilonewton, and this one is going to be 17.03. Okay, that is for the reaction, and B sub x is 0. Now, the next step, we can draw the shear diagram, moment diagram from what we have. And you may start by setting up this one gonna be x meter, this 0, 15, another 20, and you have this one for shear kilonewton. And when you do this, you're going to use the graphical method to help you, right? By using the graphical method that you have, you're going to have the first one. You may review that. The first one we have is what? dv by dx equal to w. No, equal to minus w. And then if you do the integration of this, you may have what? V sub b minus v sub a. V to the right minus v to the left equal to minus of area of w between a and b. Okay, and the third one, the downward p, going to have the delta v minus, and the other opposite. So you move to here, you have 17.03. So you're going to have upward P. So delta V is going to be positive. So you move here, you have upward. Okay, and if up to your scale, what scale you may use? If you use 1 millimeter for 2 kilonewton, okay, you divide this one by 2, that is going to be 8.5 millimeter. That is going to be 8.5 millimeter. About this. That is going to be plus 17.03. And then you move up into this, you may have the dV by dx equal to minus 4 all from A to B. So this one going to be minus 4. The dV by dx is going to be minus 4. And what is going to be the value of this? This is point B. We're going to have what? V sub B here, minus this one, minus 17.03. That's going to equal to the minus sign of the area from A to B. So this is we 4 times 4 times 15. So this V sub B gonna be minus 60 plus 17.03. Okay, and if you put that, is going to be equal to minus 42.97 kilonewton. That's okay, and this is going to be what? That is going to be divided by 2. That's 21 millimeter. Okay, and then you have this, and this is point of zero shear. This is minus 42.97, and then you get the slope of minus 4, and minus 4. Put this one there. Okay, and then you arrive here. This is 100.2. So this is gonna be 50 millimeter. So this one gonna put something like this. Okay, up. And what we have here is minus 42.97. And then you go to plus is by 100.2. Okay, and you're going to arrive this one with 57.23. 57.23. This is going to be 57.23. And then you move down here. When you move down here, you have the S dV by dx equal to minus 4. And it's going to be about here. What we have here is what? The V here. We don't know V here. Minus here. Minus 57.23. And it's going to be equal to the negative. To negative of what? Of the area here. That is going to be 4 times 10. Okay, that is going to be 40. So UV is going to be 17.23. That is going to be divided by 2. That is 8 millimeter. This is the value of here. And if you may like, just put this one, and this one to be here. And this one and this one to be here. And now, what next? You arrive at 15. So you don't get downward, right? Okay, it's going to get downward. of 17.25 minus 15, so it's going to be 17.23 minus 15 is going to be 2.23. This is going to be 2.23. And then again, you come here, slope is going to be minus 4. And you see this is 37.77. It's going to take this portion up, okay, up by this one up. So this one is minus 37.77. You may use this relationship to check it if you like. And this one gonna be something like this. And again, S is gonna be minus 4. Okay, and you may put this one minus 4, and minus 4 if you like. And this is the point of zero shear. Okay, that is the shear diagram for this beam. And next, we're going to draw the moment diagram. And before the moment diagram, this is the roller, this is the roller, and there is no applied moment here. So if you draw the moment diagram, these 2 points gonna have zero moment. Okay, zero moment, no external moment. There is no moment here. And this is the x meter. This is 35. This is 15. Actually, this is 30. And this is 0. And before we go further, we're going to determine this. And the x here can be determined by the triangle 17.03 divided by x equal to 4. So you may have x equal to 17.03 divided by 4. And then if you do the calculation, this is going to be 4.2575 meter. Okay, and you may find this distance. This is 15 minus this. This is going to be 10.7425 meter. Also, we need to determine here. Again, this is 2.23 and divided by, let's say, x, and then it's going to be 4. Now, x is going to be 2.23 divided by 4. And if you like to put into your calculator, you may get this one of 0.55575 meter. Okay, this is very small, about 0.56 meter. Okay, draw the moment diagram. You got to check the shear diagram. That's why we consider that. And you move from here to here. And what we have for the shear diagram is dV by dx. We have first one, dm by dx equal to v. And you also have the second, m sub b minus m sub a equal to area of v diagram between a and b. Okay, and the third one, we use this one. If you have clockwise moment, your delta m gonna be positive. We use this. We don't have external moment, so we have 0 here and 0 here. And next, you move from where? You move from here to here, and then you have this one. So the dm by dx here gonna be 17.03. This one gonna move upward, and by doing this is 0, so the slope here is 0. Okay, and the value of moment here is what? From here, m here, m here, minus here, minus 0 is gonna be the area here. It's gonna be 1/2 of 4.2575 and time 17.03. If you push this, you got the moment of 36.25. So the m here is 36.25 kilonewton meter. Okay, and I forgot to put this one as the m. This is m, kilonewton meter. So it's going to be 36.25. You may put the scale of 10 kilonewton meter per 1 millimeter if you like. That is going to be about 4 millimeter, 3.6 millimeter. So the slope is going to be here. The shear here is 0, so we have dm by dx equal to 0, and we have this one as the 36.25, and we have the curve like this. And now the curve gonna reduce, okay, reduce to until we arrive here. We don't know the moment here yet, right? So the moment at B, m sub b is here, it's now here, minus here is 36.25 m on the left, so sorry, m on the right, minus m on the left equal to the area here. And that is going to be 1/2 of 10.7425, and time this one, and time minus 42.97. So your m sub b from here is going to be equal to 194.55 194.55. Okay, and that is going to take about 2 centimeter, close to 19. Okay, so about here, and you have the slope here. The s over here is going to be this one, okay, minus 42.97, and then your curve is going to be something like this, and this is going to be the point of 0 moment. We can determine it later. Now this is the slope of this, and what is going to be the slope of this side? The slope of this side is gonna be the value here. That is positive 57.23, right? So this one is going to have the s equal to plus 57.23, so it's going to be up. Okay, and what is going to be here? It's going to be somewhere here. What is going to be the moment here is the m at this point, minus m at this point. This is going to be minus 194.55 minus of minus 194.55, and it's going to be what? It's going to be this area. Okay, it's going to be 1/2 of 17.25 so 3 plus this one 57.23. This is going to be this area 57.23. okay, and over here it's going to be 10 meter, right? So times 10. You put this, you may get the moment of 177.75. Okay, that is around 18 millimeter. That is going to be here. And this have the value of 17.23. okay, that is going to be, we have this one 17.23. so the slope here, S going to be 17.23, and then you're going to have the curve, something that's similar to this, and this is going to be 0. okay, and then on this side, this is 2.23, so the slope here is going to be 2.23, and this is 0 over here, 0, S equal to 0. And what is the value of the moment here? You can determine it by m here minus 177.75 m here minus here, and it's going to be this value of area here. It's going to be 1/2. It's going to be equal to 1/2 of what? 0.5575 and times 2.23. You may get m here equal to 178.37. okay, you got that, right? So you have this, and then it's going to get to 0. This is going to be the S here. S equal to minus 37.77. So slope from here 0 is going to do. So the curve is look like this, and you may have this is slope here and this is gonna be the slope here, and it's really complicated in the area here. Okay, and you may also have the slope here, and if you like, this is gonna be the slope of 0. The slope will tell you the shape of the curve. Okay, so you got what you have here. Now you may think this one is going to be positive. Okay, this one is negative, and this one also be positive. Basis on this, you may draw the elastic curve, okay, of this. Okay, may come here a little bit down. Let's make this one a little bit zoom out. Okay, if you zoom this one out, it's going to be a little bit clearer. What do we have is we have the point of inflection here and also here. So the beam going to change the curve. Okay, the curve at this point, and you may have this one as the upward, and up to here the curve change for upward to downward, up until here, and then it's changed to upward. And I believe this one is supposed to be larger than this one because the force here is larger and the span here also larger. So that's supposed to be the elastic curve of this beam. And you have this one as the also called the IP or inflection point. If you may zoom this one, we have this one as the inflection point, and you also did have this one as the IP. IP important because if you design the reinforced concrete beam, the inflection point will change, is the point that you will change the reinforcement for the beam. Okay, next, if you more specify on this, you may have this one of theta A and this one for theta C, and you also may have this one for theta B, and you can determine them if you like by using the conjugate beam or by using the unit load method if you like. Okay, that means we can do that. Okay, and what we missed from here is write down some explanation from what we did before. So we have 5. After we know the reactions, we draw the shear and moment diagram by using the graphical method, and we did. Okay, and next we draw the elastic curve of the beam. Okay, and draw the reinforcement if the beam is RC beam. Okay, as mentioned here, just come back to here. Now we are ready for that. Okay, and then we have what? We have this one as the support, this one for the inflection point, this one for the inflection point, and what we have is this is the roller, and this is the pin. Okay, and you also know that usually we have the reinforcement all the way here first, so we can put the stirrup effectively. And now for the negative moment, okay, we got to put, sorry, for the positive moment, you got to put the reinforcement like this. Okay, don't forget to have some development length here. So the bond between the concrete and the steel will be fully bonded, and this also. Okay, this is for negative. For positive moment. For negative, you just put it on the top. Okay, that is the reinforcement for this. And if you like, you may also consider the shear diagram, and you may draw some stirrup that you like to, and you may see the shear diagram vary along the length of the beam, and you may see this portion of the beam may have large shear. So if this portion have large shear, you may put more stirrup here, and for this area have less shear, you put less stirrup here. So by this one, you may put a lot of stirrup. It depends on your calculation. Actually, you can determine the spacing and the size of the stirrup. There are equations in the reinforced concrete design that you can use effectively to find it. Okay, and the other portion, okay, and then it gets larger, so just put more stirrup here, and also this is more shear. Okay, that is going to be the reinforcement of our beam. Ideally. Okay, that is the whole thing we have for this problem. That you may use the consistent deformation to analyze the statically determinate beam. Since we have 1 degree of indeterminacy and we use the force method, so we set the B sub y as redundant force, and then we consider the deformation of this beam by separate the beam into these two. One, the primary beam subjected to the applied force, another one subjected to the redundant, and then you may consider the deformation 0 equal to delta sub b downward and minus f sub b b sub y, and then you have this equation that's used to find the redundant b sub y. Then you determine the delta sub b and f sub bb by the superposition method, and then you got the delta sub b and f sub bb. You put into this equation, the b sub y is 100.2, and then you know this, you can determine a sub y, c sub y, and after that you just put into this beam to draw the shear diagram and moment diagram by using the graphical method, and with the very good scaling. Okay, your drawing going to be very beautiful. And then finally, you also can draw the elastic curve here. You got the inflection point, and you may also draw this reinforcement. Okay, and if you like to find the inflection point, you just cut the beam to this point, and your beam subjected to distributed load here. And if you remember, we have the force here of 17.03 kilonewton. Okay, and this one is x. So by doing this, we can determine we find the location of inflection point. Okay, so you cut here, you have the moment here, you have the shear here, the moment is going to be 0. So if you summation of the moment equal to 0 here, this shear have no effect, right? So you put this one as the positive. So M this way. This one going to be 4x, and this one going to be x over 2. So it's going to be plus 4x times x over 2. And it's going to equal to this one 17.03 times x. So this cut into 2 and x cut. So you may have x equal to 17.03 divided by 2. And you may have this one for 8.515 meter. This one 8.515 meter. So you have this, okay, at 8.515 meter from here. And for this one, you also can find it. Okay, you have the reaction here of 37.33. Sorry, 37.77 kilonewton. And you also have this 4 kilonewton per meter. 4 kilonewton per meter. And at the median, you have 15 kilonewton. Okay, again, the moment here gonna be 0. And then if you take here, you can determine the distance x here easily. So you can get the location for the inflection point that you change the reinforcement. Okay, that's all we have for this example, and I hope you will go back and trying to do everything by yourself. Okay, do a lot to make yourself more skillful on what we should know and have. Okay, that's the end of the clip.